15 amp 2-pole breaker is the correct type of breaker for a 220 volt 15 amp circuit. A double pole single throw 15 amp switch is suitable as a disconnect for the air handler unit. It is generally acceptable to use the same circuit that powers the air handler for the outlet and low voltage transformer, provided that the total current draw does not exceed the circuit's ampacity. For the outlet, use a 14/3 cable to provide a neutral for the 120 volt requirement of the condensate pump. For the transformer, use a 14/2 cable to provide power to the transformer. In this case, the neutral is not required. The outlet and 4 for the transformer should be mounted on the air handler in a location that is accessible for maintenance and servicing. When sizing the branch circuit for the air conditioner, several factors must be considered to ensure the electrical system can safely and reliably handle the load. Firstly, the nameplate on the air conditioning equipment specifies the minimum circuit ampacity. This value represents the minimum amount of current the circuit must be capable of handling. The conductors used in the branch circuit must have an ampacity equal to or greater than this minimum circuit ampacity. Secondly, the nameplate also indicates the maximum overcurrent protection device size, typically a circuit breaker or fuse. The overcurrent protection device protects the circuit from overloads and short circuits. The size of this device must not exceed the maximum specified in the equipment nameplate. Thirdly, when calculating the branch circuit load, it is essential to include all components connected to the circuit. This includes the air conditioning compressor, fan motors, and any other electrical components. Each component's current draw should be added together to determine the total load in the circuit. This total load should not exceed 80% of the branch circuit's ampacity, ensuring a safety margin and preventing overheating. Fourthly, the National Electrical Code, or NEC, provides guidelines for sizing branch circuits for air conditioning equipment. NEC Article 440 covers air conditioning and refrigeration equipment. It outlines the requirements for conductors, overcurrent protection, disconnecting means, and other aspects of the electrical installation. Consulting the NEC and following its guidelines is crucial for ensuring a safe and code-compliant installation. Fifthly, the conductors used in the branch circuit must be sized appropriately based on the calculated load and the applicable ampacity tables in the NEC. The ampacity of the conductors must be equal to or greater than the minimum circuit ampacity specified in the equipment nameplate. Factors such as conductor type, insulation rating, and ambient temperature must be considered when determining the correct conductor size. Sixthly, the overcurrent protection device, whether a circuit breaker or fuse, must be sized to protect the branch circuit conductors and the air conditioning equipment. The overcurrent protection device should be sized no larger than the maximum specified on the equipment nameplate and should be coordinated with the conductor ampacity to provide adequate protection against overloads and short circuits. Seventhly, the disconnecting means, typically a disconnect switch located near the air conditioning equipment, must be rated to safely interrupt the circuit's current. The disconnecting means should have an ampacity equal to or greater than the branch circuit's ampacity and should be readily accessible for maintenance and servicing. Eighthly, it is important to consider voltage drop in the branch circuit, especially in long runs. Voltage drop occurs when the voltage at the equipment terminals is lower than the source voltage due to the resistance of the conductors. Excessive voltage drop can cause the equipment to operate inefficiently or even malfunction. To minimize voltage drop, the conductors should be sized appropriately, and the length of the branch circuit should be kept as short as possible. Ninthly, grounding is essential for ensuring the safety of the electrical installation. The branch circuit must be properly grounded to provide a path for fault current to flow back to the source, tripping the overcurrent protection device and preventing electrical shock hazards. The grounding conductor should be sized according to the NEC guidelines and should be securely connected to the equipment grounding terminal and the grounding electrode system. Tenthly, it is important to follow all applicable codes and regulations when installing the branch circuit for the air conditioner. Local codes and regulations may have additional requirements beyond those specified in the NEC. Consulting with a qualified electrician or electrical inspector is recommended to ensure compliance with all applicable codes and regulations. When installing electrical wiring, it's crucial to adhere to several safety precautions to prevent electrical shocks, fires, and other hazards. Firstly, always turn off the power to the circuit you're working on. Locate the appropriate circuit breaker or fuse in the electrical panel and switch it to the off position. Double check with a voltage tester to ensure the circuit is de-energized before proceeding with any work. Secondly, wear appropriate personal protective equipment, or PPE, including safety glasses, gloves, and insulated tools. Safety glasses protect your eyes from debris and sparks, while gloves provide insulation and protect your hands from electrical shock. Insulated tools prevent current from flowing through your body if you accidentally come into contact with a live wire. Thirdly, never work in wet or damp conditions. Water is an excellent conductor of electricity, so working in wet environments increases the risk of electrical shock. Ensure the work area is dry and free from moisture before starting any electrical work. Fourthly, inspect all tools and equipment before use. Check for damaged cords, cracked insulation, and other signs of wear or damage. Do not use any tools or equipment that are not in good working condition. Replace or repair any damaged items before proceeding with the work. Fifthly, use the correct size and type of wire for the application. Refer to the National Electrical Code, or NEC, and local electrical codes for guidance on selecting the appropriate wire size and type. Using undersized wire can cause overheating and increase the risk of fire, while using the wrong type of wire can lead to insulation breakdown and electrical shock hazards. Sixthly, make sure all wire connections are tight and secure. Loose connections can cause arcing, overheating, and electrical fires. Use wire connectors that are appropriate for the size and type of wire being used, and ensure they are properly tightened to provide a secure connection. Seventhly, follow proper wiring techniques when making connections. Strip the insulation from the wires carefully, without nicking or damaging the conductors. Twist the wires together tightly and securely before inserting them into the wire connector. Ensure that the wires are fully inserted into the connector and that the connector is properly tightened. Eighthly, label all wires and connections clearly. Use wire markers or labels to identify the purpose of each wire and connection. This will make it easier to troubleshoot problems in the future and prevent confusion when working on the electrical system. Ninthly, double-check all work before restoring power to the circuit. Inspect all connections, wires, and components to ensure they are properly installed and secure. Use a voltage tester to verify that there are no shorts or ground faults. Only restore power to the circuit after you are confident that the work has been done safely and correctly. Tenthly, if you are not comfortable working with electricity, hire a qualified electrician to do the work. Electrical work can be dangerous, and it is important to have the necessary skills and knowledge to do it safely. A qualified electrician will be able to perform the work safely and in compliance with all applicable codes and regulations. When selecting a disconnect switch for an air handler, several factors must be considered to ensure it meets the requirements of the application and provides safe and reliable operation. Firstly, the disconnect switch must have an amperage rating equal to or greater than the full load amps or FLA of the air handler. The FLA is the amount of current the air handler draws under normal operating conditions. The disconnect switch must be able to handle this current without overheating or failing. Secondly, the disconnect switch must have a voltage rating equal to or greater than the voltage of the air handler circuit. The voltage rating indicates the maximum voltage the switch can safely handle. Using a switch with a lower voltage rating than the circuit voltage can result in insulation breakdown, arcing, and other hazards. Thirdly, the disconnect switch must be horsepower rated if the air handler has a motor. The horsepower rating indicates the maximum horsepower of the motor the switch can safely control. If the switch is not horsepower rated, it may not be able to handle the inrush current of the motor when it starts, which can damage the switch. Fourthly, the disconnect switch must be suitable for the environment in which it will be installed. If the switch will be exposed to moisture, dust, or corrosive substances, it must be enclosed in a weatherproof or corrosion-resistant enclosure. The enclosure must be rated to protect the switch from the specific environmental conditions it will be exposed to. Fifthly, the disconnect switch must be readily accessible. The NEC requires that disconnect switches be readily accessible, meaning they must be located in a place where they can be easily reached without having to climb over obstacles or use tools. This ensures that the switch can be quickly turned off in an emergency. Sixthly, the disconnect switch must be lockable in the off position. This allows maintenance personnel to safely work on the air handler without the risk of someone accidentally turning the power back on. The switch should have a provision for a padlock or other locking device to be installed. Seventhly, the disconnect switch must be clearly labeled to indicate its purpose. The label should identify the air handler the switch controls and should be visible and easy to read. This helps prevent confusion and ensures that the correct switch is turned off when servicing the air handler. Eighthly, the disconnect switch must comply with all applicable codes and standards. The NEC and other local codes and standards provide requirements for disconnect switches, including their construction, installation, and labeling. Ensuring that the switch complies with these requirements is essential for safety and code compliance. Ninthly, the disconnect switch should be installed in a location that is protected from physical damage. The switch should be mounted in a way that prevents it from being accidentally bumped or damaged by equipment or personnel. If the switch is installed in a high-traffic area, it may need to be protected by a barrier or guard. Tenthly, the disconnect switch should be inspected regularly to ensure it is in good working condition. The switch should be checked for signs of damage such as cracks, corrosion, or loose connections. Any damaged or worn parts should be replaced promptly to prevent switch failure and ensure safe operation. When running electrical wiring, it is essential to follow a systematic approach to ensure safety, efficiency, and compliance with electrical codes. Firstly, plan the wiring layout before starting any work. This involves determining the locations of outlets, switches, light fixtures, and other electrical devices. Consider the needs of the space and plan the wiring to meet those needs. Create a wiring diagram to help visualize the layout and ensure all connections are properly planned. Secondly, obtain the necessary permits before starting any electrical work. Most jurisdictions require permits for electrical work to ensure compliance with electrical codes and safety standards. Contact your local building department to determine the permit requirements in your area. Failing to obtain the necessary permits can result in fines and delays. Thirdly, gather all the necessary materials and tools before starting the wiring. This includes wire, connectors, electrical boxes, conduit, fasteners, and tools such as wire strippers, pliers, screwdrivers, and voltage testers. Having all the materials and tools on hand will help you work more efficiently and avoid delays. Fourthly, turn off the power to the circuit you will be working on. Locate the circuit breaker or fuse that controls the circuit and turn it off. Verify that the power is off by using a voltage tester to check the wires in the electrical box. This is an essential safety precaution to prevent electrical shock. Fifthly, install the electrical boxes and conduit according to the wiring plan. The electrical boxes provide a safe enclosure for wire connections and protect the wires from damage. Conduit protects the wires from physical damage and provides a pathway for running the wires through walls and ceilings. Secure the boxes and conduit properly using appropriate fasteners. Sixthly, pull the wires through the conduit and into the electrical boxes. Use a fish tape to pull the wires through the conduit. Leave enough extra wire in each box to make connections easily. Be careful not to damage the wires when pulling them through the conduit. Seventhly, make the wire connections according to the wiring diagram. Use wire connectors to make secure and reliable connections. Ensure that all connections are properly tightened to prevent loose connections and arcing. Follow the color coding for wires to ensure proper polarity. Eighthly, ground all electrical boxes and devices properly. Grounding provides a path for fault current to flow back to the source, tripping the circuit breaker or fuse and preventing electrical shock. Connect the grounding wire to the grounding screw in each box and device. Ninthly, label all wires and connections clearly. Use wire markers or labels to identify the purpose of each wire and connection. This will make it easier to troubleshoot problems in the future and prevent confusion when working on the electrical system. 10thly, inspect all wiring and connections before restoring power. Check for loose connections, damaged wires, and other potential problems. Use a voltage tester to verify that there are no shorts or ground faults. Only restore power to the circuit after you are confident that the wiring is safe and correct. When installing a low-voltage transformer for an air handler, several factors must be considered to ensure it is properly sized, installed, and protected. Firstly, determine the voltage requirements of the low-voltage devices that will be powered by the transformer. These devices may include thermostats, control relays, and other components. Identify the input voltage required by these devices, typically 24 volts alternating current, or VAC. Secondly, calculate the total volt-amp, or VAR, load of all the low-voltage devices that will be powered by the transformer. Add up the VA ratings of each device to determine the total VA load. This will help you select a transformer with sufficient capacity to power all the devices. Thirdly, select a transformer with a VA rating that is equal to or greater than the total VA load of the low-voltage devices. It is generally recommended to choose a transformer with a VA rating that is slightly higher than the calculated load to provide a safety margin and prevent the transformer from overheating. Fourthly, choose a transformer with the appropriate primary voltage to match the supply voltage available at the installation location. The primary voltage is the voltage that the transformer will be connected to, typically 120 volts AC or 240 volts AC. Ensure that the transformer is compatible with the available supply voltage. Fifthly, mount the transformer in a suitable enclosure to protect it from physical damage and environmental factors. The enclosure should be made of a non-combustible material and should be adequately ventilated to prevent overheating. Choose an enclosure that is rated for the environment in which it will be installed, such as an EMA3R enclosure for outdoor locations. Sixthly, wire the transformer according to the manufacturer's instructions and all applicable electrical codes. Connect the primary voltage wires to the appropriate terminals on the transformer, and connect the secondary voltage wires to the low-voltage devices. Use appropriately sized wire connectors and ensure that all connections are tight and secure. Seventhly, provide overcurrent protection for the transformer primary circuit. Install a fuse or circuit breaker in the primary circuit to protect the transformer from overloads and short circuits. The size of the fuse or circuit breaker should be determined based on the transformer's primary current rating and all applicable electrical codes. Eighthly, provide overcurrent protection for the transformer secondary circuit. Install a fuse or circuit breaker in the secondary circuit to protect the low-voltage devices from overloads and short circuits. The size of the fuse or circuit breaker should be determined based on the total VA load of the low-voltage devices and all applicable electrical codes. Ninthly, ground the transformer enclosure and all low-voltage devices properly. Grounding provides a path for fault current to flow back to the source, tripping the overcurrent protection device and preventing an electrical shock. Connect the grounding wire to the grounding screw in the transformer enclosure and to the grounding terminals of all low-voltage devices. Tenthly, test the transformer and low-voltage devices to ensure they are operating properly. Use a voltmeter to verify that the transformer is providing the correct secondary voltage. Check the operation of the low-voltage devices to ensure they are functioning as intended. If any problems are detected, troubleshoot the wiring and connections to identify and correct the issue.